So I will tell you a bit about what we did in this ERC project I had about graphs and data integration. I think it's a good follow-up from Kian's talk. You will see that there are some commonalities and some big differences. So if you look back, in terms of information management, there was in the past a strict separation, right? When I was a PhD student, basically you had kind of the DB view of the world and the IR, information retrieval part of the world, right? And they were very distinct. The text and IR was basically, you know, Google, if you wish. It was mostly search using an inverted index. And as the kind of mean to get the information, you would use keywords. And on the structured data side, very different. You had like Oracle, let's say, or DB2, a DBMS, a database management system, and a declarative query language to ask your question, for example, SQL. And today, if you remember this, this old story about the different V's of big data, I will be telling you stories about the third V, right? This is the basically, you know, the variety, right? The integration part of big data. And information or data or service integration, believe it or not, is still the biggest problem out there, right? In terms of costs, if you look at the Gartner reports, it's a very big deal, right, to integrate systems. And if you think about it, how do you, let's talk about data, right? How do you integrate data? This is a field which is almost as old as computer science. Typically, I say that you need some kind of mediation, right? If you have two systems, you need some kind of mediation to integrate those two systems. And this mediation can be one of those two systems, or it can be a third-party kind of entity, right? So if you talk about text, in the past, really, this integration, it was all about keywords, right? You would like search keywords, and then you would retrieve documents which contain those keywords. That was the mediation. Then we had what we call syn sets, right? Synonym sets, meaning that if you search for automobiles in Switzerland, you also have cars in Switzerland, or voiture in French. So, you know, like synonyms, words which have the same meaning. For structured data, guess what? We've been working on this also for decades. What we used to do, and we still do it, by the way, right? What's the state of the art in database integration? It's what we call a global schema, right? So you have different databases. They are all related, but they don't use the same schema. What you will do is create a super schema. We call this the global schema. That's the mediation. And then you will relate the global schema to all the local schema through views. This is called local as view or global as view, right? Depending on how you use the views, and then you can automatically translate a query to a local or to a global query, depending on how you do the syntactic translation. What you can do also, by the way, is not have a global schema, but a set of mappings between all of these to create kind of a mapping of schemas where you can translate the different queries, right? This is called like peer data management, if you are interested into this. And guess what? All of this is very, very difficult. And what do all the companies want to do these days? They want to do one and two at the same time, right? Because if you think of any reasonable company, they will have tons of structured data from databases, from web tables, from internal systems, from SAP. And they will have tons of semi-structured and unstructured data, contracts, emails, web pages, etc. Right? So how can you basically provide a solution to those companies? The answer recently has been entities, right? So we come back to this knowledge graph idea. The idea is to store information at a slightly higher entity granularity, and then to integrate information through links. right? And this is a small example from Google. Google did this a bunch of years ago, and they are still very big in that context, where you have, you have one, in this graph, you have entities like Barack Obama, and then you have relationships between them, right? And this is, I think, a very natural way of integrating information. When I talk, by the way, to medicine people and like neurology experts, they tell me that the brain does a bit the same, it seems, to relate entities, right? It has like those connections. Compared to keywords, I would argue that it's higher level, right? You're not talking about the syntax, like car, automobile, those words. You're talking about a higher level concept, right? And compared to database systems or traditional relational systems, it's messier, right? It's what we call denormalized. You don't adhere to strict rules. You don't always have a good schema for this. This is very heterogeneous, also very sparse. You might miss many of those links. But this is much simpler as well, right? Meaning that you don't have complex queries to go from Barack to Michel. You simply follow the link. So you don't need to have joins, you simply follow links, right? And this has many drawbacks. We can talk about this during the break. By the way, this is still, I think, a very prominent way of integrating data in big companies. You know that, companies like, I was telling you, Google or Amazon, they use this a lot. But to give you other ideas, in Switzerland, big companies use this a lot, like Roche, Novartis, the big pharma companies, they have hundreds of people working on this to integrate the data. Also the banks in Switzerland, all kinds of big businesses use this internally normally, right? Those knowledge graphs, they are not available to the public. And what's the idea in terms of like high level, view on this? This is the idea, right? You have basically an entry point, which is like global, consistent to relate all kinds of information in a company, right? So you have this kind of global view using a knowledge graph. And then you can query this knowledge graph these days, either using, let's say Sparkle or a graph query language or an LLM. And then you can get all kinds of pieces of information from different sources relating to the entity or the concept or the relation you are looking for. Okay? So I guess it's very intuitive. We worked on this for, oh my gosh, quite some years in my lab. We built different big data pipelines to do this, mostly from text to entities, because that's the hardest part, right? And we used to have like fairly, scalable, but also classical ways of doing this. Kien was mentioning this a bit, right? You do entity recognition, linking, entity typing, co-ref resolution to basically build those links from unstructured or semi-structured sources to this knowledge graph to then be able to dive in from any kind of higher level app. What I want to tell you today a bit, I want to dive in a bit into two technical aspects that we've been exploring recently and that are very important in this context. I will tell you a bit about what we did in terms of crowdsourcing. This is called today human in the loop, right? This is very important for any kind of big data system. And I will also tell you a bit about representation learning, how we can use AI, machine learning actually, to help you in this task of relating all the information of a company to a knowledge graph. Let me start with crowdsourcing and human in the loop, right? This is no secret, though people don't discuss this so much. But in big tech companies and very big companies doing that kind of work, they have hundreds and hundreds of humans. Usually they are either, hired as external employees or they are from a different company, but like Google and those guys, Amazon, they have hundreds of people looking at this to make sure that the quality is okay. Right. So we think that this is still today with the LLMs, it's very important to have like data you can trust. Otherwise, this game of inferring things can rapidly go sour. So I will tell you, for example, about one kind of classical paper I would argue that we did some time ago. It's called Zen Crowds, to solve this problem of relating text to a knowledge graph, right? What is Zen crowd? From a technical perspective, IR perspective, it's a three-stage blocking approach. What is blocking? It's when you have too many combinations and you try to restrict the number of combinations of your, in this case, like links you are drawing. So it's basically, an inverted index to get candidates of the links, but then we use algorithms and humans to verify those links. Okay, and how do you use humans? We are not Google, so we don't have like hundreds of specialists we can ask to do this. So we used Amazon, right? Amazon Mechanical Turk. I guess you all heard about it, right? Amazon Mechanical Turk is a micro-task crowdsourcing platform where you can dynamically publish tasks that humans will do. And why do they do that, the humans? To gain a bit of money, right? Every time they answer in a reasonable fashion a task, they could get a few cents, a few bucks, depending on how you reward them, right? And then we combine all of this using probabilistic network, so it's a bit of Bayesian inference. So here is the big level idea. What we did is we took HTML pages. We took HTML pages from the New York Times, from some newspapers in India, and from Swiss Info, which is like information about Switzerland, right? Just to try different sources. And then we have this automated pipeline where we will extract the entities. An entity is, it's what we call a surface form, right? So it's a bunch of text, bunch of keywords that relates to something which is in the knowledge graph, right? So I don't know who this person is, I cannot guess. But anyway, an entity, for example, in terms of the surface form could be Joe Biden, which is fairly simple, right? Joe Biden, you relate this to Joe Biden. But it could also be, for example, the President of the United States. And guess what? This is already much more difficult, because which president? And is it a real president or is it a fiction? Perhaps it's not even a real president, So in many cases, this game of finding the entity, the surface form, and relating it to the knowledge graph is much more complex than it sounds, right? And I think you can relate to this, because many of those problems, they sound easy when you think about it. And when you look at all the cases, it can be very, very difficult, right? Sometimes you don't even know as a human. So what we do is we try to extract those surface forms, and then we will try to match them automatically to some of those nodes, right? And then you have three cases. Either you're pretty sure. We use different, by the way, algorithms to do that, and then we kind of vote. And if most of the algorithms, they agree, Joe Biden relates to Joe Biden, the president of the United States, then you're done, basically, right? You can write this link in your data system. Okay. The other extreme case is where you have no idea. Right? Let's imagine that in the knowledge graph, you don't have the president of Switzerland. Yes, we do have presidents in Switzerland. And I can buy you a coffee if you can name, without looking on your machine, who is the president of Switzerland right now. Anyway, so let's imagine we don't have the president of Switzerland in the knowledge graph. Then you give up, basically, right? You have an issue, you cannot guess who this person is in the knowledge graph. And then you have the cases in between, where you have the president of the United States, and some algorithmic matchers, AI matchers these days, they will tell you, oh, this is Joe Biden, and some other matchers will let you know, will say, oh, no, this is Donald Trump, okay? And what do you do in that case? You ask humans. So what we do in those cases, we have this big probabilistic network. We will publish a task on Mechanical Turk, like a web page dynamically, asking humans to check this. So we give them how it works, we give them the text, we give them the different possibilities, and they have to vote. Looking at the text, oh no, this is definitely Joe Biden, right? Because this is an article from last year or whatever. So we use this human in the loop crowdsourcing to do that. And every time the human clicks, we record this in our probabilistic network, and then we do inference, Bayesian inference. And it's a big, probabilistic game where if you trust some of those matchers, if you trust some of those humans, then you will infer with a high probability. It's like, majority voting, but on steroids. Oh yeah, this sounds to be really like Donald Trump or whoever in this case, and then you write this link. Okay? Does it work? Of course it works, since we are cheating to some extent, right? We are using humans to help us create those links. But it's not as easy as that. What we've seen, for example, is that this is the precision of the workers, right? When I say workers, those are the humans. This is the precision of the humans, right? And first of all, you see that the precision is kind of a mess, right? It's not 100%. Why? For many reasons, but we give them the hardest cases. Sometimes those cases have no solution, and sometimes also they make mistakes, obviously, and sometimes they do it rapidly just to get the money, right? But what I want to tell you is, first, you have some very good workers. Like, this person is outstanding, right? He did like 300 of our tasks with a 80% accuracy. So that's the kind of worker you want to keep on your platform. And we have algorithms for that, by the way. The second part is that this looks bad, but it's not that bad, because typically we give 5 choices, right, to those people, like 4 choices plus none of them. And on average, right, if you randomly guess, 0, 2 is probably somewhere here. So you see that even if the humans make mistakes, they are still much better than a random guess. So this is still usable. And then what the game in this probabilistic reasoning is not to trust blindly all those workers, right? But to understand step by step who the good workers are, and to rate them higher, right, in terms of the confidence. And then you can really gain, a 20% accuracy by doing this. And I don't have time to get into the details, but we did this for a bunch of other tasks, right? We use this human-in-the-loop approach recently also for debugging noisy training data, right? I think that's what many of the big companies do also. They don't tell you this, but they will use those hundreds of human workers to really either get additional training data or to debug the training data that they have, right? They do a bit of active learning. They understand which pieces of data are really important, and they will have humans correcting this. And you have a bunch of companies which do that for you as well, right? If you're interested. We also use this human-in-the-loop approach to aggregate answers, where you have different kinds of answers, you can aggregate them. And we use this to detect events. That's one of the use cases I will talk about at the end of my talk. And also to classify things, but with an explanation, right? That's something we did recently, which, by the way, I like a lot. This was published at AAAI a couple of years ago. It's, when you have a model which is not explainable, usually the deep learning models, they are not explainable, right? You can add human explanations and train a model with this, and then you can try to guess some explanations from those human explanations that you added to the model. Okay, the second technical idea that I want to pass on to you in terms of this link creation is, I would say obviously these days, representation learning, right? What is representation learning? It's a big part of AI and machine learning these days. It's how do you represent something into vectors in the end, right? And it sounds easy and is not. Guess what? You understood that it took us computer scientists really decades to understand how to transform text into vectors, right? Guess what? It's the same for graphs. Graphs are very complex, as I was saying yesterday, and it's still not clear today how you transform graphs into vectors. Right? So projecting nodes of a graph onto a vector space while preserving key structural properties of the graph. Okay, that's a bit the task that we tackle. And this is easier said than done, because obviously projecting means losing information, and structural properties, this depends on your application. Right? Whether you want to have first-degree neighbors or other kinds of properties that you take from the graph and you translate into typically vectors, right? In a high-dimensional space of like unknown strict dimensions. And people have been doing this quite a bit these days for link prediction, typically. So this is the same basically problem I was telling you about. You have Oh no, this is a different problem. You have like the source and the object, the target, and you want to know what is the label of this edge. Or we also have been doing instance completion, right? You just have the subject and you try to guess both the property and the object, right? You can also try to guess only the object, right? That's a bit what we were doing in the previous example. What about knowledge graphs? This is much more difficult than other kinds of graphs, like biology graphs, for two reasons. Knowledge graphs, at least in the big companies, they tend to be very, very large. So you need something scalable. And usually those embeddings, we call this embedding, as you know, right? Those embeddings are not scalable in terms of constructing the embeddings. And the other issue, which people never realize, is that knowledge graphs are very, very expressive compared to most graphs. Why? For a bunch of technical reasons. First, the knowledge graphs, usually they have tons of different kinds of nodes, right? They have nodes with known types, and they have many different types. So we call them heterogeneous graphs for this. Also, they are labeled. Usually, the edges have labels, the nodes have labels, and typically they have some sort of logic, right? So for this, you should ask Ken, but basically most of those graphs, they have some kind of description logics behind in terms of how you can work with those edges and types. So this is very, very difficult to basically represent some basically aspects of a knowledge graph into vectors. So what we've been doing in my group is tackling those different technical problems one at a time. So for example, we worked a lot, and I think we are not there yet, in terms of those heterogeneous graphs embedding, like having an embedding, but which captures the different types of the nodes. Right, so we've been working for this for years by starting with slightly simple graphs and then going crescendo to basically have not only in terms of the information you capture in the embeddings, not only the graph structure, but also the node types. Okay, why do you want to know that? Because node types are obviously key in a knowledge graph, right? Those are key information. What we've been doing also is second order kind of information gathering. This is called hyper-relational graphs. When you have basically, this is a triple, right? Marie Curie academic major was physics. This is another triple. Marie Curie academic degree was a Master of Science. But then sometimes you have facts about facts, right? And when you have those facts about facts, you need to represent this as a hyper-edge. What is a hyper-edge? It's an edge which basically do not only go from one node to another node, but from a bunch of nodes potentially to another bunch of nodes. Okay, and this is very much present in knowledge graph, if you know a bit knowledge graphs, through materialization, right? You have different ways of writing this. This is very much present, by the way, in Wikidata also. Right, you have those facts, not about a node, but facts about a triple. So we've been working also on capturing this in the knowledge graph and in the embeddings. And finally, we've been working on very large scale knowledge graph embedding by using probabilistic structures called sketching. So you might know sketching, right? This is a way to basically get some information about some of the data, but in a probabilistic fashion. What's the advantage? It's much faster. So we got like very good speed up by using sketching to do the embeddings instead of having more specific and strict ways of doing this. And you can use those approaches not only to get basically the labels of the link, that's what everyone is doing, right? But you can do this also to complete the instances, right? So basically, if you are missing fact in your knowledge graph, you can use this to infer some fact in the knowledge graph. You can do this also if you have a schema or a taxonomy to basically automatically complete the taxonomy. I was telling you, perhaps the president of Switzerland is missing in your ontology, you can use such techniques to get those information automatically. And you can also use this for semantic text tagging, right? That's what we presented actually this year at dub. Like, you have a very large ontology, you have a very large corpus of text, you will tag with the ontology parts of the text. Okay, so I don't know if this sounds like conceptual or not, but believe me, if you wish, this is very much applied actually, right? And this is used a lot, those techniques, in a production system. So I will tell you 3 examples where we actually helped people solve their problems with those techniques for real use cases that we have deployed. The first one is science-wise, and I'm very sad because we had money to sustain this project for years, but now the money ran out and this website is not accessible anymore. But I can tell you what we did. We did this with scientists, like physicists, and I know nothing about physics, but as you know, in Switzerland we have the CERN. We have this large collider, right? And we have like hundreds, thousands of physicists working on this. And they came to us and they told us, okay, we have a big problem. And this is actually, by the way, a very common problem. We have too many papers published, right? I guess you can relate to that problem. I don't dare looking at archive what papers have been published recently, because I know I will not have time to look at them. Right. So that's what they told you in physics. And we said, okay, we can help you. Do you have a kind of an ontology? Do you have a taxonomy of physics? And guess what? The physicists, they have a taxonomy, right, in their field. We use this taxonomy and we built this system. Actually, we partnered with Archive. We would get for every new article in Archive, we get automatically all the data. We would pass the data like we did for the New York Times and automatically create links. It's exactly what I told you before. Right, between, let's say, this new paper I have no clue about, nonlinear electrodynamics as a symmetric something, right? We look at the abstract, look at the text, and create a link between this and concepts in physics, electrodynamics, partial differential equation, causality, okay? And then physicists could basically use this system, register their, either their papers or their interests, and they would receive every day or every week a digest of all the papers which are related to this. Right. So this was actually a very nice project, and again, I'm very sad that we didn't get enough money to sustain it, because guess what? You need money to still, again, human in the loop, like engineering, to sustain such things. But I will tell you a second project which is still alive. This is what I did with the Swiss government. This is called event detection on social streams. So the Swiss government, like many governments, I guess, they are always interested in breaking events, right? Because they have cells to react to breaking events. And what are those events? The use case they always gave us is like a plane crashing, right? If a plane crashes, you want to immediately react, right? And like publish something on the web or react to this catastrophe. Or politician dying, same issue. If you have a prominent politician dying, the Swiss government is going to express their condolences, blah, 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 right? Or obviously, that's worst, right? The terrorist attack. If you have a terrorist attack, you want to know immediately what's kind of going on the social networks, right? And typically, those social networks, they are the first to get the story, right? If you remember those horrible like attacks in Paris, it was very much first Twitter at the time who had all the information. People were tweeting all those events, right? And the Swiss government, guess what they did? They tried to analyze Twitter using keywords. And as we all know, it's very difficult to analyze text with keywords, and it's worse for tweets. Because in the tweets, right, you will not have, like, if a politician died, you will not have those keywords, politician dying. You will have, oh, I'm so sorry that someone disappeared, passed away, blah, blah, right? So you cannot do those keyword match. This is not good enough in terms of what we call recall, right? In terms of getting enough information. And knowledge graph can help. Why can they help? Because we have very good information about those entities in the knowledge graph, right? If you take Wikidata, you know the politicians, right? I'm sure Wikidata knows who is the president of Switzerland. They have very distinct information about all of this. So that's what we did. I will give you an example, right? We take tweets, and we do exactly the same game as what I told you just before, right? We will enhance the tweets with links to knowledge bases. And again, this is a bit cheating, because once you do this, you have solved the problem, because you have so much more contextual information about what's in the tweet, right? So for example, you have this tweet here. Where is it? Yeah. Edward Brooke, first black senator since Reconstruction, dies at 95. So if you can relate this, let's say, Edward Brooke to where he is, I'm a bit lost in this, but to basically, you know, here you have Birmingham, and you have some nodes in DBpedia about Birmingham. So you can rapidly understand that, you know, this person is a politician, he passed away. We have WordNet to understand, you know, all those synonyms in terms of passing away, disappearing, etc. And then you can really get, what can you buy with this? You can get all the context about this tweet, and you can understand if this tweet relates to the events you want to identify or not. And then when you have a positive match, we issue it in the system, and we compute those positive matches. And if there is like a peak in those matches, then we send this to the analysts in the Swiss Confederation, right? And guess what? We got a huge boost in performance. We are basically 10 times better than their system, right? And again, it makes sense. It's because we have additional information about all those entities. And thanks to this knowledge graph integration, we can understand a bit what's inside those tweets. And last one is very different. Last one, I hope you will like it. We also had a lot of fun working on this. It's actually about my favorite topic, infrastructure optimization. So we worked on Microsoft Cloud. To basically help them. So what's the idea here? As you know, Microsoft, they have a very big cloud, Azure, and they have hundreds and thousands of machines. And it's very difficult to understand what's happening inside those machines. Why? Because each machine creates logs, but each machine runs tons of services with different logs. And then you have all those logs on disk, right? And this is like, you know, petabytes of logs daily. And how do you use those logs? That's a good question. Thanks for asking. Basically, you have very smart engineers who will write, you know, Cosmos kind of scripts, or think about MapReduce, right? They will have some kind of higher level way of taking the logs, or what they call cooked logs, like snippets of logs or like summary of logs, and then they will write a very big parser to parse those logs, wait half an hour, and then they will get some kind of insight about what's happening, right? This is very time intensive. This is very power hungry in terms of the resources, and this takes a lot of time simply, right? Because you have to iterate and you have to manually kind of check those logs, which are arcane, those logs, right? It's very difficult to understand those logs. So what we did is, guess what? Exactly the same idea, but we didn't work on tweets or research papers. This time we worked on the log themselves. And the log, they can be, if you simplify, like in two different formats. They can be text, right? You've all seen text logs, but sometimes they can also be binary, right? So I had a student actually working at Microsoft and doing those parsers to automatically, for each kind of log, try to understand which are the entities and which are the links, and then creating a graph from this log, right? So that's the same idea. We defined a schema, right? And then we had some parsers to automatically relate logs and create this knowledge graph, to populate these knowledge graphs, right? So you have petabytes of logs daily, and then at this graph layer, you have a graph which is much smaller. By the way, it's still very large. We still have many issues storing this graph because this was very large. But you know, this is like, let's say, a terabyte, right, of graphs. And with this graph, you can do exactly what we do with such knowledge graphs. You can directly ask questions using a graph query language, right? You can ask questions about, oh, why is this job failing? What is this customer doing? What happens if I move this customer to a different cloud, right? You can ask all those questions, not from petabytes and petabytes of very complex logs, but directly using this natural high-level graph. That's the system that we build as a kind of case study, and then Microsoft actually productized this, right? So they use this for the productized version for auditing compliance, for job scheduling, for job ranking, for migrating customers. So I was very happy to see that then this had really an impact on Azure, on GDPR, and on their systems, basically. Okay, I think I should stop here. I was fast. I hope this was not too fast. To conclude, please remember a few points. Data integration, it's a very big deal, right? We don't talk about it enough in the science community. This is still the most expensive problem in IT if you at least ask the very big companies, right? So it's an excellent playground for researchers. You have tons of very hard problems, so perhaps you should work on this. And second thing is that you cannot today do this automatically, right? This data integration is still a very, very complex topic. You probably need human computation. You need humans to check this, and probably you need a lot of machine learning also to help because the scale can be quite daunting. So I think we really need more people working on this to have like expressive, effective, efficient method in that context. Thanks a lot.